mostly going to be more focused. Shut up. The class takes like a long note. It's not. It's easy stuff. It's just going through it. But also, people have a million questions left. I feel like the script tends to be a little more. This sounds like a little more. Oh gosh, this is recording. Thank you. Whatever. I'm gonna own it. The script tends to be a little more on the ball, which is fine. There's no shame in being less on the ball. There's no shame in being more on the ball. This group just tends to be a little more comfortable with past lessons. So now I'm going to edit all this out. It's just nobody's going to feel good watching that, right? Like, because we actually do homework. Yeah.
Well, do they have access to our stuff?
It'll take them a little more time to figure out how many.
I mean, yeah.
Yeah, exactly.
I got it within time.
Okay. The end of the year, because you've hit this point where, like, slowly over the course of a semester, people go from being here like 5 minutes before the bell to like as the bell's ringing, like half the class is here. Do you know? I had a year ago or 2 years ago, I guess a year ago, I had an afternoon after lunch. I had an advanced functions class, and they liked not attending early. They liked to like go for lunch, and so when the bell rang, I would lock all of the unused chairs in the science office. And then, if they came late, they had to stand for the duration of the period. And I kind of liked that. Anyway, I'm not. No, at this point, it's just a story. But
I feel like you're boring.
no, here's the deal. The difference is that was on like day 7 of a semester. We are conspicuously, hey, day 74 of a semester.
On top.
And that means that we have a mere 12 days remaining. Guys, don't let me forget, at the end of the period, by the way, today's lesson is not a difficult one, but it's I just said not difficult. Who is possibly objecting to that? Hands up if you have a problem with a lesson that's not difficult. Just let me know.
Oh, definitely.
Yes.
You always say it's not difficult, but then it's difficult.
That's not true. Don't we talk about this? Aren't you the one who's always like, I don't know what. I don't. Three things. First,
Here we go.
First, you're always like, oh, this is so difficult. I'm so bad at it. I'm going to fail. And then it's like, I got 95 on my test.
Okay, that's not how it goes.
Well, that's kind of how it goes. That's not how your voice sounds, but that's basically how it works. Second, the tangents are intentional. I like them. They make me happy. But more to the point, if I just did pure science for 60 minutes, you'd have a headache at the end and you wouldn't have learned anything. It's actually a pedagogical technique. It's truth. Just sometimes you need to think, they're not all intentional. Some of them are legitimate ramblings of an addled and confused mad cow-filled mind. But most of them are very pointed. Today's lesson is not difficult, but I discovered that the last class just took their time with it. I don't think they found it particularly tough, but it went slower than I would have liked.
Don't be that kid. Don't be that kid.
Don't get
Put your hand down. Put your
You
hand
said there was
down.
3 things, we only said 2.
The third, no, and this time I actually do have a third. The third is at the end of the lesson. Miss Smith is putting on for her senior classes the forensics activity, and she asked if we would participate. So we're going to. Stop. We're going to. It's actually going to be a lot of fun. More to the point, it is going to be a nice simple worksheet that you should fill out and pretty much all get perfect on. And it's going to be a nice little bonus mark to your lab section. So there you go. Maybe I'll even put it in the assignment section because that's where people's marks are a little lower. We're just going to make it a nice little chance for you to pad your mark with a nice easy one. Yeah.
an activity or a worksheet?
It's both. It's an activity with a worksheet.
Don't
Yes.
worry, you have both sides.
Have you marked it?
Have you found mine?
Yeah.
I haven't looked yet, if I'm being honest.
I guess I should hand those last week.
Yes. Now,
I looked on Etsy and none of my labs.
are they not? Okay. Well, you know, we'll get that. Look, it doesn't. Listen, I got a lot on my plate right now. I'm doing my best to manage my time. There's no suggestion that I'm doing so perfectly. Perhaps that's something you can relate to. Doing my best.
Gotta have
In the
steak
meantime.
before the salad.
I'm not good at time management.
What?
I have the steak before the salad.
Okay.
You
Anyway.
don't want it to go cold.
Okay. Sure. That's true. Or your salad to get warm, though. Either way, you lose something. That's what life is. Life's a series of
No,
compromises.
but seriously, think about it. Cold salad, like, it's so better than warm.
Oh yeah. Salad's got to be crisp and cold. Moving on. Today we are talking about another way of looking at redox reactions. Now a redox reaction is short form for what two types of reactions?
Reduction, oxidation.
Reduction and oxidation.
No.
Bam. No, he's good. He's that quick. So these reactions always happen in tandem. If a reduction reaction is happening, it means that what is happening?
Was gaining electrons.
Yeah, it means that some chemical species is gaining electrons. For that chemical species to gain electrons, there must be a readily available supply of electrons. And if that is happening, then a reaction must be happening somewhere else where electrons are being lost, right? So if one reaction is gaining electrons, another must be providing them, losing them to satisfy that. Now, conspicuously, you'll note that in all of the reactions we've looked at so far, you haven't seen any electrons, have you? Right? We looked at balancing reactions and we talked about oxidation numbers, but even though these reactions are all about electrons, we've yet to actually see the electrons in a reaction. So today's method of looking at redox reactions will allow us to see what's happening with the electrons because we're going to break one reaction into two parts, and we're going to look at the oxidation reaction on one side, and we're going to look at the reduction reaction on the other side. So we're going to break a whole chemical reaction, specifically the one you see up here, into its half reactions. Hence the title of the lesson, half reactions. All right, lesson. So what is the first reaction here? What is, let's say this, what is the, I don't know, what's the oxidation reaction here? Which species is being oxidized? What do you think? Well, we have two species, right? We have iron, and we also have chromium. Chromium's a little funky to look at because it's part of a compound on the left, but let's look at the iron. What is happening to the iron here? Yeah, this too should definitely be up top. That's frustrating. Let's just take that and you would never know. It's invisible, that change. Okay, so what is happening to the iron here? Well, if we take its half reaction, iron 2 plus is becoming
Iron 3 plus.
iron 3 plus. So is that an oxidation or a reduction? Oxidation, good. What is the other half reaction? It's definitely the reduction because there's always one of each. At least you can actually have reactions where there's multiples of each happening, but there must be at least one thing being oxidized, one thing being reduced. So what's being reduced? The Cr, and its half reaction is that it starts out in a chromate ion, like this, and it ends up all by itself with a charge of 3 plus. Good. So that's the first step. And again, we're belaboring this because I want to make sure it makes sense to everybody. These steps come quite quickly. So the first thing is to identify what the two reactions are. And then we need to balance them. Now, the iron reaction is already balanced. There's one iron on the left. And how many irons are on the right? One. So in terms of atoms, it's balanced. Yes? Well, we're going to talk about that. It must be. If the one is being oxidized, the other must be reduced. In the next step, we'll talk about specifically how it's reduced. Is that a fair answer to just say wait? Okay. Now, for the second reaction, is it chemically balanced? Do the atoms balance? Obviously, we can't balance the oxygen yet, but is the chromium balanced? No. What do I need to make it balanced? Is that fair? Okay, now, the next step in this, so the next step is to look and say, for these reactions to occur, one is an oxidation reaction, one is a reduction reaction. What is actually happening to them? They are either losing or gaining electrons. Now we're going to put the electrons in to these equations. Yes.
So the previous step, why don't we include oxygen in balancing the equation?
How would you balance it? What number would you put in front of something on the right side to balance the oxygen?
Nothing.
Yeah, you can't yet, right?
But
We have to wait until we've put something in the reaction that has an oxygen, and then we will make sure we balance the oxygen. And it's going to be water. But does that make sense? Yes, we are definitely eventually going to have to balance oxygen, but at the stage we're at, there isn't any oxygen in the reaction, so I can't balance it. Right? We have oxygen on the left side.
Yeah.
Is there any oxygen on the right side? No. So we can't balance the
So
oxygen.
why isn't there oxygen? If it's
Because the oxygen is no longer bound to the chromium on the right side. We're going to figure out where the oxygen goes.
okay, so right now we're saying we don't know where it goes.
That's right. I mean, spoiler alert, it's going to become water, but,
Yeah.
but that's right.
Okay.
So again, it's just like Jessica's question. It's a case of when you get to the end, you'll see why we do it in the order we do it. Now, yes.
I'm just confused with why, like, I'm really confused with, like, both of these are losing electrons, right?
No.
Numbers are increasing?
No.
Are increasing?
The charges are increasing, but chromium's charge isn't increasing. On the left, it's with 7 oxygens, each which has a -2 charge. Just trust me, work with me. We're going to do the easy example first, then the tough one, and then you'll go, oh, I get it. And it'll be a light bulb moment, and it'll be great. Yeah, and we'll totally be like, yeah, that felt good. That felt good. I'm glad we get this now. Don't whisper about me. Secrets don't make friends. Okay, now, I want to look at the iron. Fe2 plus, shh. Fe2 plus becomes Fe3 plus. Don't write this yet. Or do, relax, God, relax. Relax. If you wrote it, you wrote it. But before we write about it, let's think about it. What must happen here?
Lose one electron.
It's going to lose an electron. So how do I write that into the equation?
Minus one electron.
Where is the electron going to end up?
Oh.
Does an electron go on the left side? Is this reacting with an electron? Or does it go on the right? Is it producing an electron? Good. So on the right-hand side, and this is why if you already wrote it, it doesn't matter. I just thought we'd chat about it first. It releases an electron. Because iron's oxidation number was 2 plus, and on the right side it becomes 3 plus, and for that to happen, it must give up an electron.
Oh, never mind, okay.
It's
Oxidation number. I would love that. That's actually a great idea.
I'm still confused, and I want you to answer the question when it gets to that point, and I want you to know when I get it.
I would love that too.
We need like.
What?
Just
a light bulb?
I know, I love that. Got it. Okay, now we're going to talk about the right side, and hopefully this will clear the air.
I would love it if this was a pencil sharpener.
You need like a that was easy button.
What do you want to ask?
Oh, no, she answered it.
Good. Okay, good. Okay, so on the left side, this is an oxidation reaction. Oxidation means losing electrons, and this one is fairly clear, right? Iron has a charge of 2 plus. It comes to the right side, it's oxidized, meaning it gives up an electron, and it becomes iron 3 plus. And we knew that it was 1 electron it lost because its oxidation number changed by 1. Had this become iron 4 plus, it must have lost 2 electrons. If it had become iron 5 plus, it would have lost 3 electrons. This is nice and easy because it's just a charged ion to a charged ion, which makes finding the oxidation number easy. right? You can just visualize that. On this side, finding the oxidation number is a bit more obtuse. What is the oxidation number of chromium here? Well, let's take a look. The whole thing has to add up to, the whole thing has to add up to -2. Good. Now, oxidation number of -2. That provides a total of -14. But the whole thing has to be -2. So if the oxygen provides -14, how much positive do we need to get to -2? 12. Good. Each chromium, therefore, speaking. Yeah, on the way.
You can tell we have a supply.
No, it's not.
This is gonna get old quickly.
You can tell
Okay.
it's a supply.
So listen, the difference must be 12. So each chromium must have an ox of 6+. Because the whole thing must have an oxidation number of -2. Each oxygen is -2, and there's 7 of them for a total of -14. So we have to get back to -2. That requires +12. The chromiums are the only thing there that can be doing that. So the chromiums are +12, but how many of them are there? 2. So each one must be +6. Now, on the right side, what is the oxidation number of chromium? Okay. So what's the change?
Are they working as
It sounds that way. I believe they may be mining. It's possible that they're digging into the depths of the earth to recover precious metals. Now,
So
what is
Thursday
what
we have
is
one
the
more.
change
We have
then?
miners.
Yeah, so this must be gaining 3 electrons per chromium. So gains 3 electrons per chromium. Per chromium. Each chromium has an oxidation number of 6 plus on the left and an oxidation number of
3+.
3 plus on the right. Good. So chromium needs 3 electrons. But do we have just 1 chromium? We have a total of 2. So how many electrons do we need total? Tap 6 times if the answer is 6. Minor. Oh, there we go. See? He's, yeah, he knew. He knew. It would actually be a really interesting, like, experiment to know. By the way, are these electrons going on the left or the right? Left, because they're being gained.
That gains.
Come
It'd be a
in.
really interesting, like, sociological experiment to count how many taps, like, per thing, and see if there's some kind of pattern, or is it completely random?
Only you would think of that.
I don't think only I would think that. That doesn't fascinate you?
No.
Oh, sorry, Kelsey. This chair is really bothering me.
I like-
hitting the wall.
I like to think that one's just going to pop out of the cupboard. This is no, but that's how they used to invade. Like even in the First World War, they dug tunnels to other trenches, and then they would plant explosives under the trenches.
Yeah, then they would find you and they
This is
blow
true.
it up.
So I can only assume that one of my many arch nemesis is coming to get me, and he's taking the only logical way he can think of, which is coming under my classroom, and then he's going to explode the place. That's the only thing I can think of. Okay, now.
The Kool-Aid man jumps through the wall.
Pretty funny. Okay, now, Sorry?
I'm not sure what you said, but I thought it was very different than what you said, I think.
The Kool-Aid Man. You know the big jug of Kool-Aid with arms and legs and a mouth on the front? I don't want to. I thought for a brief moment I wanted to try to figure it out, but on further consideration, I'm cool not knowing. So, okay, look here. Now, we have two reactions. In the first reaction, iron becomes 2 plus, becomes iron 3 plus, and releases an electron. Is this electrically balanced? Is the charge balanced? How could we check? How could we check? I have yeses, I have nos, often from the same person. How could we check if the charge is balanced? Yeah, we can add them up. What's the charge on the left side? 2 plus. What's the charge on the right side? 2 plus. Right? Because we have the iron that is 3 plus, but then we have the electron that is -1. So the sum of the charges on the right side is 2 plus. The sum of the charges on the left side is 2 plus. So this is electrically balanced.
Go get a stress ball from Jack.
No.
What?
He exploded it up there.
But if we look at the right side,
No.
is this electrically balanced? Well, in fact, what's the total charge on the left side? -8. What's the total charge on the right side? Almost.
Plus 6.
I made the same mistake last period. It is -8 here, and then this is +3, but how many of them are there? 2, so it's a total of +6. Good. What's the difference between the two? 14. Now, just like atoms have to be balanced, because we can't create or destroy atoms, we said electrons have to be balanced, because we can't create or destroy electrons, but charge also must be balanced. We cannot create electrical energy and we cannot destroy electrical energy. We can just move it from place to place. Which means if we look at this, it is physically impossible to have -8 as the total charge on the left and +6 as the total charge on the right. The only way that can happen in real life is if we annihilated, destroyed electrons, or annihilated and destroyed protons. That's a nuclear reaction, neither of which is happening. So this must be balanced.
Why? Why wouldn't the electrons just go in, like, bond something else?
They can, but we have to show that. And that's what I'm saying. This is exactly what you're asking before. We now have to ask, what must be involved from the surrounding environment for this reaction to happen? So that's exactly it. So right now, that -8 charge we start with has to go somewhere.
Okay.
What are you going to take a negative charge with? Well, this is in acidic solution. So what are your options?
Water.
Water or H plus ions. Which one is going to help us balance charge?
Water.
No,
H plus ion.
H plus ion. Because they have what kind of charge?
A negative.
Positive.
Positive. So they will cancel a
Negative.
negative. So looking at this, where should we put H plus ions to make it balance?
On the left.
On the left. How many will we need to put on the left? 14. Good.
14. Oh my god.
Oh my God. Okay.
Okay, Christopher Walken.
Okay, well,
Okay, this is neither accurate nor conducive, so be quiet. Okay, that would be a
The day hell froze over.
Yeah, tell me about it.
All right, and now
I don't think it qualifies.
And now the charge is balanced. Now on the left side, we have a total charge of +6. And on the right side, we have a total charge of plus 6.
But we need water.
Let's talk about it. We're happy right now. Can't we just be happy for a minute
Never.
before the next thing?
No.
You're totally that. Sorry? Do you want me to walk through how we got to here?
No.
Honestly, I'm going to use my 5.1, 5.3.
Okay, then we'll talk one-on-one maybe.
Just the 5.1.
Yeah.
I think you missed
And
this.
it's not like what's
I think it, is it not? Are you sure?
I don't think so. Maybe.
I checked. I have a
No, it's
Oh,
not.
it isn't. I will change that. Maybe I'll do it right now so I don't forget.
even the first one.
There's nothing that has USB-C.
Except newer phones. Or the MacBook.
No, but there's like.
Go away. I don't want to watch myself.
Muhammad Ali?
Yeah, he died.
No. Yeah, he's dead.
Yeah, he died.
Yeah, he died on the weekend.
I heard that he was died.
Okay, guys. Yeah, shut up.
Oh, I know what it is.
Okay, there we go. The video's on the now. Anyway, okay. Shh. So let's do a quick review of what we've done so far, and then we'll do the next step. We have taken the reaction up top, which is an unbalanced redox reaction, and we've split it into reactions. We've said that this really is iron being oxidized, being reduced. And now individually, we said that those reactions have to be balanced for like the key element. In other words, if I have one iron on the left, one, it's balanced. But here, chromium on the left, I need to make sure I have 2 chromium on the right. That was the first step. Is that fair? Okay. Now in the next step, we said that the whole point of a redox reaction is that it's the gaining and the loss of electrons. That's why we're doing all this nonsense, is so we can see what happens with the electrons. So this step is really the important one, where we now say, to what's happening to this iron, we have to track the electrons. If which goes from 2 plus to 3 plus, how many electrons does it have to lose to make that true? Oh, just 1, right? 1 electron will take something with a 2 plus charge, and if we take the electron away, we now have a 3 plus charge. Is that clear?
Yeah.
This side's tougher.
Yeah.
This side is tougher. What we need to figure out is what is chromium's oxidation state inside this complex. And we do that, I mean, just review the third page of 5.1. It talks about finding oxidation numbers. So when we do that, we see that chromium has an oxidation number. When we do the same on the right side, we see that it has an oxidation number, the second, 3 plus. But it has gone down. It's been reduced by 3 electrons. Now the only thing to remember is how many chromiums do we have? 2. So for a total of 6 electrons. So if we take chromate and add 6 electrons, we can get chromium to its right oxidation state. That's assuming that the oxygen's oxidation state doesn't change, which it doesn't. Unless you have a compelling reason to know otherwise, oxidation state is always
Oxidation state.
Thank you, that was very useful. So now, in the last step, we say for these reactions to be true, they have to be electrically balanced, because you can't create electrical energy, you can't destroy electrical energy. So, for the first one, it's not an issue. Fe2 plus balances perfectly with Fe3 plus and an electron. There's a 2 plus charge on both sides of the equation. That's fine. But this one didn't balance perfectly. On the left side, we had 8 negative charges. On the right side, we had 6 positive charges. So there's a big difference between those two. And we say, since this is happening in an acidic solution, what can balance it? Adding acidic hydrogens. And we add more negative. So for this reaction to happen, yeah, it takes 6 electrons, but it will also require 14 H pluses. The charge. In other words, for something to go from being negative overall to being positive overall, we need to provide some positive charges. And electrons alone won't do that, obviously. We got 14 by looking and saying the left side was -8, and the right side was positive 6. The difference between that is 14, and that's where we got that number. How's that feel? A little better? Good. And again, the tricky part of actually figuring out what the oxidation number was here, that's just a matter of practice. Look again at 5.1, do the homework for 5.1. Lots of practice on that. Okay. Now we're on to the last step, which is, again, iron becoming iron with an electron next to it is already perfectly balanced. We don't need to do anything with that. So this is fine. But the equation on the right is not a balanced chemical equation. Because for this equation to be true, we would have to have 7 oxygens and 14 hydrogens that just disappear. Do oxygens and hydrogens just disappear? No. So what must those oxygens and hydrogens do?
Make a lot.
They come together and they make water. How many waters can I make from this? 7. So we're just going to rewrite the equation in a way that reflects that. So we're going to say that if we take that chromate ion, add 6 electrons, and add 14 H pluses, we can make the 2 chromium ions that we want, but we also are going to make 7 waters. Oh, that's better.
So why do we care?
Okay, again, the reason we care is that what redox reactions are really about is electrons. Reduction is the gaining of electrons, the adding of electrons. Oxidation is the loss of electrons. As such, it is incumbent upon us, we need to have a version of these chemical reactions that show us what happens with the electrons. And the balanced chemical equation won't. When I combine these two, the electrons are going to cancel out because all the electrons that are released by the iron are gained by the chromium. Sorry? Okay. Yes?
Why is it in 7 water?
Because we have 7 oxygens and 14 hydrogens, and they have to go somewhere. So they're going to come together. And how many waters can you get out of 7 oxygen and 14 hydrogens? Well, every water has 2 hydrogens, 1 oxygen. 7 oxygens is enough for 7 waters, and 14 hydrogens divided by 2 is enough for 7 waters. And that's balanced. Yes?
Will this 2-to-1 ratio always be like
Yes. If a reaction really can happen, the ratio will work out. Good question, by the way. All right, now, the last step would be to say, how many times does this oxidation reaction have to happen to be able to make this reduction reaction happen? How many times? So the reduction takes a chromate ion and reacts at 6 electrons and 14 H pluses to give us chromium 3+ ions and water. How many times do we have to do this before this can happen? 6. Where does that number come from?
The amount of electrons.
Good. How many electrons do I need here?
6.
How many electrons get released here?
1.
Just 1. So if I need 6 electrons, I need to release 6 electrons. To release 6 electrons, how many times do I have to do this? 6 times. Again, this feels long and drawn out because we're talking our way through it. The question would take you about 5 minutes once you know what you're doing and sitting down doing it. So not long questions. I know they feel like it, but they really aren't. So the last step is if we want to, we can combine these into a single reaction again. Because you don't always want to. Sometimes we do want to look at the half reactions in isolation. I guess if I want you to. Is that a better answer? All right. So 6 times the oxidation reaction can give us the reduction reaction. So let's do that. If I do this reaction 6 times, what will I have to write? Oh, that's not what I want. 6Fe 2 plus.
Plus
And then is there anything else on the left side?
CR2.
No, we're just going to look at this one first. And then on the right side, I'll get what?
Oh.
6Fe3 plus.
Good. If you already wrote the CR207, you're going to write it eventually, so don't stress out. And how many electrons?
6.
Good. What color should I use?
Purple.
Red.
Good. I like purple. Okay. Black. Black, like, wow.
Black is a shape. not a color.
No, it's a
Oh,
color.
okay,
It's-
Liam.
Liam, shut your trap.
It's a color.
Jessica, back me up on this.
Nobody gives a damn.
It's a color.
Not
It's
enough.
a shade.
That's something that,
I
like,
see how it is.
that's like the clever thing like grade 6 students say before they say, like, tomatoes are actually fruits. I got news for you. All vegetables are fruits. So get over it.
Like, really?
Of course.
Oh yeah, that's true.
We got
Of course
a
they
C.
are. You know who draws the distinctions between fruits and vegetables?
Us.
Grocery stores. It has no basis in biology. They're all the same thing.
Brussels sprouts.
You don't want a vegetable.
My good old cucumbers.
I don't care. I'm so mad.
Now listen, I have looked at Smith's smoothies and I
And you
can
didn't bring
guarantee
a
you
strawberry.
there's some vegetables in that thing. Also, God knows what else.
Of course.
Now,
It looks like
Okay.
bodily fluid.
shh. Cat tranquilizers, the whole thing. Yeah,
Bird liver must be spotted.
that was inappropriate. That wasn't an appropriate joke I just made. Anyway,
We're missing an arrow somewhere.
yeah, I'm gonna make it blue.
Oh, he's changing the color.
Yeah, because the colors have to do with which side they came from, right? The arrow doesn't come from either side.
You're making our notes.
Yeah, nice purple.
garbage.
Okay, now
What does it look like
again,
up there?
the reason we break the purple actually stays pretty consistent. Now, the reason we break this down into halves is to see what the electrons are doing. Because you will notice now, when I simplify this equation, what's going to happen?
Yes.
The electrons have to cancel out. They always will in a redox reaction. However many electrons we give up on one side are going to be gained on the other side. So the electrons will always perfectly balance. They have to. That's how redox reactions work. But breaking it into half reactions first lets us see what happens with the electrons. And that's why we do this. That's why this way of balancing an equation. By the way, sometimes you will also have to balance H pluses and waters at this point. Do we have to do that here? No, there's nothing to cancel, right? All the H pluses are on the left, all the H2Os are on the right. So we're happy. And so the final balanced chemical equation for this would be 6Fe2 plus Yeah, hearing this, I'm reminded how much I'm glad I don't have a job that actually involves, work.
Thursday we had lawnmowers and weed whippers, leaf blowers. Now we got miners.
Because sometimes I find myself thinking like, oh, I missed I worked at a golf course one summer. That was fun. And then you go, was it fun? Or am I just telling myself that because it was 16 years ago and I don't know. I feel like I had fun.
It
Anyway.
probably was fun 16 years ago. But if you were to do it today, it wouldn't be fun.
Oh, my back.
I have fun at work. I mean, I just get all the young people to do stuff. And I drive
You are
the
young.
I mean, well played, but no, false. Okay, so this is a second way of balancing this. Now, you could have balanced this using the way we learned in 5.2. Both are acceptable methods. You will find that when you actually get doing these, it doesn't take much longer. The advantage of this method is that it allows you to see what the electrons are doing. I don't think I have time to go through example 2. So what I'm going to do is this. At lunch, I'm going to record it, and you guys are going to watch on your own time. You get filled in. It's no different, just like last time when we do this reaction in basic solution, there's one more added step, pluses with
OH negative.
OH minuses, and that's it. So hey, okay. Oh, she sent me that link. Did I close it? I probably closed it.
No.
Steven, yes. Yes.
I have an action for it.
Okay, well that felt inappropriate to me. Rather than show this video, because I feel like so again, tomorrow, participating in this culminating forensics activity, and here's the idea. There's going to be a crime scene.
Oh my gosh, just because Kyle is dead.
I don't know. Kyle, are you going to be dead?
I don't know.
Yes.
I hope not.
Okay, apparently not so far, though things can change. But we're going to go in and we're going to collect a little bit of evidence and test it. And it's stuff. The biology class, I think, is testing the blood typing. I need to make those chemicals today because I'm reminded. We are testing for residue copper to determine what the murder weapon was.
Sorry.
So it's kind of a cool thing. It's fun. Again, there's going to be a little worksheet to fill out. We'll be filling them out as a lab group, not individually. And it's just an opportunity, A, to pad your mark a bit. And I put that one. I don't have a category set aside for this because it's not, they've developed it there. It's not a big thrust of my course. So I didn't want to make it, in the mark book because that wouldn't be, I think, an honest representation of what I've put into this or sort of made it part of my course. But I want it to be an opportunity for you guys to participate in something that my coworkers have put a lot of work into. I think done a very nice job with. But also pad your marks, which is a nice thing. So I will kind of figure out where it's going to have the nicest impact, whether that would be in the lab section, most likely in the assignment sections. That's probably where I'll put it. And it'll just, it'll sit there. We'll do it during this period, so you don't have to be taken out of class at any other time for things like that. It's also, if I may, you to see, in a highly artificial setting, but at the same time see what chemists really do in the real world. I don't know, does anyone watch Making a Murderer on Netflix? I suggest you don't, because if you do, you'll end up binge watching it in like one horrifically long, 32-hour session, like most of us. It's kind of addictive and emotionally manipulative, but that's pretty good. It's interesting. Yeah, no, they know exactly what they want you to feel.
Netflix series in general do that.
Yeah. Well, documentaries do, right? That's in their nature. It's never a completely honest reporting of things, right? It's always biased. But it's pretty good. But, or did anyone recently watch, I guess you guys wouldn't watch the O.J. Simpson thing, would you? Because O.J. Simpson.
Oh, I know.
And then I stopped watching and I missed the next episode. And
Yeah.
I watched it.
But, does O.J. Simpson mean anything to you, as a person? No, you know who he is, but, he wasn't, a cultural.
No.
When I was a kid, I was a Bills fan, so, he was, I think he still is, actually. But he's up on the wall, renowned as the greatest Bills player of all time, and he's a movie star. He's famous, and then all of a sudden, one day you saw him driving, a white Bronco down the street with a gun to his head, and it was alarming stuff. It was this big, major cultural touchstone. When I was 6, I guess, when the verdict came down, we all went down to the gym and they put it on the.
It was voted the least productive half an hour in U.S. history.
I believe that. Well, I imagine the Kennedy assassination and 9/11 probably also had similar types of reactions, but it was a big deal. It's a really, really big deal. But that case ended up turning on a lab technique. right? It ended up turning hugely on, were these samples of blood contaminated? Have they been faked? Have they been put in a vial first and then put on this glove? So there was a lot of talk about these things, and we tend to think, I think, of scientists as people who just do, I don't know, academic type stuff. But the truth is, there are all kinds of fields where you use applied chemistry, forensics being one of them. Does anyone else feel like their sanity is just being taken away, like one
Yes.
cracking out at a time?
Yes.
No.
Yes.
Can I just go?
Does anyone else feel inclined to just go to the library for the last 15 minutes?
Yes.
Yes.
I don't think I can take this much longer.
I just don't know what the hell.
Yeah, whatever. Wait, did you get in there?
We're not right about that.
Stop trying to hack my phone call.
Oh.
Do it, Elijah. It's